let yourself settle in for tonight's journey. Find that space of perfect comfort, where your body can release the weight it's been carrying all day. Take a slow, deep breath, feeling the air fill your lungs, and as you exhale, imagine all the tension flowing out of you like water finding its way downstream. Tonight, we're embarking on a voyage to the edge of everything. But you don't need to do anything except relax and let the words carry you. We're going to explore the strangest boundary imaginable, the edge of the universe itself. But this isn't a journey that requires effort or concentration. Just let the ideas wash over you like gentle waves, painting pictures in your mind of cosmic landscapes that stretch beyond comprehension. Some of what you'll hear tonight might challenge everything you thought you knew about reality. Some of it might seem impossible, even paradoxical. And that's exactly as it should be. The universe's edge isn't just far away. It's fundamentally strange in ways that make our everyday experience seem like a shadow of something deeper. So, breathe, relax, and prepare yourself for a journey to the ultimate frontier. Close your eyes if you'd like, or let them rest on a distant point. We're heading to the edge of the observable universe, and then beyond it, into realms where the very concepts of space and time begin to dissolve into something else entirely. Let's begin. The cosmic horizon, our observable edge. Stand outside on a clear night, far from city lights, and look up at the stars. You're seeing photons that have traveled for years, decades, centuries, even millennia to reach your eyes. The light from the nearest star beyond our sun, Proxima Centauri, has been journeying through space for just over 4 years. When you look at the Andromeda Galaxy with your naked eyes, you're seeing light that left that cosmic island 2.5 million years ago, when our ancestors were just beginning to walk upright across the African savanna. But there's a limit to how far we can see. Not because our telescopes aren't powerful enough, not because space is filled with obscuring dust, but because of something far more fundamental. The universe has a finite age, and light can only travel so fast. The universe began 13.8 billion years ago in the event we call the Big Bang. Since then, light from the most distant objects has been traveling toward us, racing through the expanding fabric of space at its maximum possible speed of 186,000 miles per second. You might think, then, that the edge of the observable universe should be 13.8 billion light-years away. But here's where things get strange. Due to the expansion of space itself, the most distant objects we can observe are actually much farther away than their light travel time would suggest. When astronomers calculate the true distance to the edge of the observable universe today, accounting for how space has expanded while that light was traveling, they arrive at a staggering figure. Approximately 46.5 billion light-years in every direction. This creates a sphere centered on Earth with a diameter of about 93 billion light-years. This is our observable universe, sometimes called our cosmic horizon. It's not an edge in any physical sense. There's no wall there, no boundary marker, no place where space ends. It's simply the limit of how far light has had time to reach us since the beginning of the universe. Think about that for a moment. The edge of what we can see is nearly 3.5 times farther away than the age of the universe multiplied by the speed of light would suggest. This happens because while light from distant galaxies has been traveling toward us, space itself has been stretching, carrying those galaxies farther away even as their ancient photons journey toward our telescopes. The galaxy that emitted the light we're receiving right now from the edge of the observable universe has, by this point, receded to a distance of 46.5 billion light-years. This cosmic horizon isn't the same for everyone. If you could somehow instantaneously travel to a distant galaxy 10 billion light-years from Earth and look around, you'd have your own cosmic horizon, 46.5 billion light-years in every direction from that new vantage point. Some of what you could see from there would overlap with what we can see from Earth, but much of it would be unique to that location. Galaxies and cosmic structures that exist beyond our observable universe, forever hidden from our view by the simple fact that their light hasn't had time to reach us yet. But there's another cosmic horizon that's even more profound, the event horizon. While the particle horizon marks the edge of what we can currently see based on the universe's finite age, the event horizon marks the edge of what we will ever be able to see, even if we wait forever. Here's why this second horizon exists. The expansion of the universe isn't just continuing, it's accelerating. This acceleration, driven by the mysterious dark energy that permeates all of space, means that distant galaxies aren't just moving away from us. They're moving away faster and faster. Beyond a certain distance, roughly 16 billion light-years from Earth currently, galaxies are receding so rapidly that even light emitted right now will never reach us. The expansion of space between us and those galaxies will always outpace the light's ability to close the distance. This creates a sort of cosmic prison. We can observe galaxies that are currently within our cosmic event horizon, and we can watch them for billions of years to come. But we can never send a signal to them, never visit them, never receive any information from them about their future evolution. They are, in a very real sense, disconnected from us causally, existing in a region of space-time that can never interact with our region, no matter how long we wait. The situation becomes even stranger when we consider that the cosmic event horizon is actually shrinking. As the universe continues its accelerated expansion, more and more galaxies cross this boundary, disappearing from our ability to ever contact them. In about 100 billion years, if the current expansion rate continues, observers on Earth, or whatever remains of our galaxy by then, will only be able to see the galaxies in our local group, which will have merged into one giant elliptical galaxy. Everything else will have receded beyond the event horizon, and future astronomers will look out at what appears to be an empty, static universe, with no evidence of the vast cosmic web of galaxies that we can observe today. Think about the cosmic microwave background, that faint whisper of light from when the universe was just 380,000 years old. When we observe this radiation today, we're looking at photons that have been traveling for more than 13 billion years. They come from a shell of space around us, a surface we call the surface of last scattering, located at a current proper distance of about 46 billion light-years away. But we can't see farther back than this surface, not because there was nothing before it, but because before this time the universe was opaque. In those earliest moments, the cosmos was filled with a plasma of ionized hydrogen, free protons and electrons that hadn't yet combined to form neutral atoms. Photons couldn't travel freely through this plasma. They would scatter off the free electrons, bouncing around like light in a thick fog. The universe was, quite literally, glowing from the inside. But that glow couldn't escape its own boundaries. Then, when the universe had cooled to about 3,000 degrees Kelvin, something remarkable happened. The temperature dropped enough that electrons and protons could combine to form neutral hydrogen atoms in a process called recombination. Suddenly, the fog cleared. Photons could travel freely through space without constantly scattering off charged particles. The universe became transparent. Those photons, released at the moment of recombination, have been traveling through space ever since, stretched by the expansion of the universe from visible light with wavelengths around 1,000th of a millimeter to microwaves with wavelengths around 1 millimeter. This is the cosmic microwave background radiation, a wall of light that marks the effective edge of what we can see in the electromagnetic spectrum. The oldest light that has ever reached our telescopes and that will ever reach them. But here's something that should make you pause. When we look at the cosmic microwave background, we're seeing the universe as it was 380,000 years after the Big Bang. We're looking at the baby pictures of the cosmos. Yet this baby was already about 42 million light-years across at that time. The region that would eventually become our observable universe was already enormous, already seeded with the tiny density variations that would eventually grow into galaxies and galaxy clusters. And everywhere you look around you, in every direction, you see this same ancient light, all arriving from that same epoch in cosmic history. It's remarkably uniform. The temperature varies by only about 1 part in 100,000 across the whole sky. This uniformity tells us something profound. The universe, on the largest scales, is the same everywhere we look. There's no center, no edge, no preferred direction. Every point in space sees essentially the same cosmic horizon, the same cosmic microwave background. Or does it? Recent observations have revealed subtle anomalies in the cosmic microwave background, hints that the universe might not be quite as uniform as we thought. There's a curious alignment of the largest temperature variations in the CMB, dubbed the axis of evil by cosmologists because it seems to suggest a preferred direction in the cosmos, which shouldn't exist according to our standard models. There's also the cosmic dipole anomaly, where measurements of the CMB's motion through space don't quite match up with the motion inferred from galaxy distributions. These could be statistical flukes, artifacts of how we measure and process the data, or they could be real features of our universe, hints that we're missing something fundamental about the nature of space itself. They remind us that our cosmic horizon, while well-defined in theory, still holds mysteries we haven't fully unraveled. Standing at this edge of the observable universe, peering out at the cosmic microwave background, we're confronted with a profound question: what lies beyond? If the observable universe has a radius of 46.5 billion light-years, what exists at a distance of 47 billion light-years? Or 100 billion? Or a trillion? The honest answer is, we don't know. We can't know, at least not through direct observation. Those regions are, by definition, beyond our cosmic horizon. Their light hasn't reached us yet, and depending on how cosmic expansion proceeds, it may never reach us. But that doesn't mean we can't make educated guesses, informed by our understanding of physics and cosmology. And when we do, we encounter some of the strangest ideas in all of science. The shape question. Flat, curved, or infinite? When you hear that the universe might be flat, your first instinct might be to picture it as a two-dimensional plane, like a sheet of paper extending infinitely in all directions. But that's not quite what cosmologists mean when they talk about the geometry of the universe. The flatness they're referring to is something more subtle, something that requires us to think carefully about the nature of space itself. Imagine you're an ant crawling on the surface of a balloon. From your tiny perspective, unable to see the larger structure you are on, you might think you're traveling across a flat plane. But if you keep going in what seems like a straight line, eventually you'd return to your starting point, having circumnavigated the balloon without ever encountering an edge. The surface of the balloon is curved, even though you can only move in 2 dimensions across it. Now imagine that balloon is being inflated, getting larger and larger. As it expands, the surface becomes less curved, approaching flatness in the limit where the balloon becomes infinitely large. This is something like what cosmologists mean when they say the universe is flat. They're talking about the curvature of space itself, not just the 2 dimensions we can easily visualize, but all 3 spatial dimensions. The curvature of space determines how geometry works on cosmic scales. In a flat universe, parallel lines remain parallel forever, and the angles of a triangle add up to exactly 180 degrees, just like in the Euclidean geometry you learned in school. In a positively curved universe, like the surface of a sphere, parallel lines eventually converge, and the angles of a triangle add up to more than 180 degrees. In a negatively curved universe, like the surface of a saddle, parallel lines diverge, and triangle angles add up to less than 180 degrees. Why does this matter? Because the curvature of space is intimately connected to the total mass and energy content of the universe through Einstein's equations of general relativity. If the universe contains exactly the critical density of matter and energy, about 5.9 protons per cubic meter, spread out uniformly, then space will be flat. If there's more than the critical density, space curves positively, like a sphere. If there's less, space curves negatively, like a saddle. When cosmologists measure the geometry of the universe using observations of the cosmic microwave background and the large-scale distribution of galaxies, they find something remarkable. The universe appears to be flat to within about 1%. The total density of mass and energy in the cosmos seems to be almost exactly the critical density, making space as close to perfectly flat as we can measure. This flatness raises a puzzle. In the early universe, even a tiny deviation from perfect flatness would have grown over time due to the expansion of space. If the universe had started out even slightly curved, by now it should be dramatically curved, either so positively curved that it would have already collapsed back on itself, or so negatively curved that it would be expanding far more rapidly than we observe. The fact that the universe is still flat after 13.8 billion years of expansion suggests it must have been extraordinarily flat at the beginning, fine-tuned to better than 1 part in 10 to the 60th power. This fine-tuning problem was one of the key motivations for the theory of cosmic inflation, which proposes that in its first fraction of a second, the universe underwent a period of exponentially rapid expansion, driven by a quantum field in a special high-energy state. This inflationary expansion, lasting perhaps 10 to the negative 35 seconds, would have stretched any initial curvature to essentially 0, leaving us with the flat universe we observe today. But here's where things get philosophically interesting. Just because the universe is flat doesn't tell us everything about its shape. This is because cosmologists distinguish between the geometry of space, whether it's flat, positively curved, or negatively curved, and the topology of space, which describes how space is connected to itself. To understand topology, return to our 2-dimensional examples. A flat sheet of paper and the surface of a cylinder both have flat geometry. If you're an ant crawling on either surface, parallel lines stay parallel and triangles behave normally. But they have different topologies. On the infinite sheet, if you keep walking in one direction, you'll never return to your starting point. On the cylinder, if you walk around its circumference, you'll come back to where you began, even though you never encountered an edge. In 3 dimensions, the possibilities multiply. A flat, infinite universe that extends forever in all directions is just one option. But space could also be shaped like a 3-dimensional torus, a donut, where if you travel far enough in any direction, you wrap around and return to your starting point. Or it could have an even more exotic topology, like a Klein bottle or a multiply-connected space where different regions of space connect to each other in non-intuitive ways. If the universe has one of these exotic topologies, we might be able to detect it through careful observations. If space wraps around on itself on scales smaller than the observable universe, we might see multiple images of the same galaxy or galaxy cluster in different directions. We might detect correlations in the cosmic microwave background that repeat in patterns indicating the universe is folded back on itself. So far, searches for these signatures have come up empty. If the universe does have a non-trivial topology, it must be on scales larger than the observable universe, at least 46 billion light-years or more. This leads to one of the most profound questions in cosmology. Is the universe infinite? If space is truly flat and has the simplest possible topology, just extending forever in all directions with no wraparound, then yes, it must be infinite. An infinite universe contains an infinite number of galaxies, an infinite amount of matter and energy, and infinite space itself. The implications of an infinite universe are staggering. In an infinite universe, even the most improbable events must occur somewhere, simply because infinity provides unlimited opportunities. There would be an infinite number of Earth-like planets, an infinite number of civilizations like ours, even an infinite number of exact copies of you, living lives identical to yours down to every quantum detail. In fact, if space is truly infinite, and matter is distributed roughly uniformly on the largest scales, then there must be regions of space, inconceivably far away, that are exact duplicates of our observable universe, with identical galaxies, stars, planets, and people. This idea troubles some physicists because it seems to rob our existence of uniqueness and makes the universe fundamentally unpredictable. If everything that can happen does happen somewhere in an infinite universe, how do we make sense of probability and prediction? Others embrace it as a natural consequence of the simplest possible cosmology, combined with the observed flatness of space. But there's another possibility, one that's both more conservative and more mind-bending. The universe could be finite but unbounded. This is what you'd get with a positively curved universe. Space curves back on itself like the surface of a hypersphere, finite in extent but with no edge, no boundary. Travel far enough in any direction, and you'd eventually return to your starting point, having circumnavigated the entire cosmos. Recent measurements from the Planck satellite and other cosmological surveys have suggested hints. Nothing conclusive, but intriguing. Hints that the universe might have a slight positive curvature after all. In particular, a puzzling effect in the cosmic microwave background data called gravitational lensing, where light from the CMB appears to have been bent slightly more than expected by the gravity of intervening matter, could be explained if the universe has a very gentle positive curvature. If confirmed, this would imply a closed universe, one that's finite in size but still enormously vast. perhaps hundreds of billions of light years across. The debate over the universe's true geometry and topology remains unsettled. What we can say with confidence is that the universe is either infinite or so large that its edges or wraparound points lie far beyond our cosmic horizon. Either way, there's vastly more to reality than we can observe from our particular vantage point in space and time. And this brings us to perhaps the strangest aspect of the universe's edge. It's not fixed. The cosmic horizon we see today is different from the one we saw yesterday, and it will be different from the one we see tomorrow. As time passes and light travels farther, the edge of the observable universe expands, bringing new regions of space into view. Every second, about 1 light second of previously invisible space becomes observable. Every year, a light year. Every billion years, a billion light years. But this growth won't continue forever. Because of the accelerating expansion of the universe, driven by dark energy, there will come a time, already in progress actually, when galaxies start crossing our cosmic event horizon in the other direction, disappearing from our ability to ever contact or observe them again. The edge of what we can see is, in a very real sense, beginning to shrink. The cosmic microwave background. Echoes from the edge. The cosmic microwave background is the oldest light in the universe, a fossil record of the infant cosmos, preserved in the pattern of radiation that fills all of space. When we tune our radio receivers to certain frequencies or point specialized telescopes at seemingly empty regions of the sky, we detect this faint glow. Radiation with a temperature of just 2.725 degrees above absolute zero, coming from every direction at once. This radiation comes from a specific moment in cosmic history, about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was a plasma, opaque to light. After this moment, it became transparent, and the photons that had been trapped in the plasma were suddenly free to travel through space unimpeded. Imagine being there at that moment, suspended, somehow in that ancient cosmos. In every direction, you'd see a glowing wall of light, orange-red in color with a temperature of about 3,000 degrees Kelvin, similar to the glow of molten metal. This wall wouldn't be at any particular distance from you. It would surround you completely, because every point in space was equally hot, equally dense. The whole universe was glowing. Now, as those photons have traveled through 13.8 billion years of expanding space, they've been stretched along with the fabric of space itself. Their wavelengths have grown longer by a factor of about 1,000, shifting from visible orange-red light into the microwave portion of the spectrum. Their temperature, which is intimately connected to their wavelength, has dropped by the same factor, from 3,000 degrees to just under 3 degrees above absolute zero. When we observe the cosmic microwave background today, we're seeing the universe as it was at that moment of recombination, projected onto a sphere around us at a current distance of about 46 billion light-years. This sphere is called the surface of last scattering, the last time and place where photons in the CMB interacted with matter before beginning their long journey to our detectors. The remarkable thing about the cosmic microwave background is its uniformity. No matter which direction you look in the sky, the CMB has almost exactly the same temperature, varying by only about 1 part in 100,000. This uniformity tells us that the early universe was incredibly smooth and homogeneous on large scales. Different regions of space, even regions so far apart that light couldn't have traveled between them since the Big Bang, somehow started with almost exactly the same density and temperature. This uniformity is actually a problem, or at least it was until the theory of cosmic inflation provided an explanation. If different regions of the early universe were causally disconnected from each other, never in contact, how did they all end up with the same temperature? It's like finding that two people who have never met or communicated somehow ended up wearing identical outfits down to every detail. Pure chance seems wildly improbable. Inflation solves this problem by proposing that all the different regions we see in the CMB were actually in causal contact very early on, before inflation began. They started with similar conditions because they were originally part of the same small region of space. Then, during the brief moment of inflation, this region was stretched to enormous size, far larger than what would become our observable universe. Regions that had been in contact were suddenly separated by vast distances, but they retained the memory of their common origin in the form of their similar temperatures. But the cosmic microwave background isn't perfectly uniform. If it were, there would be no galaxies, no stars, no planets, no life. The tiny temperature variations in the CMB, those 1 part in 100,000 fluctuations, are the seeds from which all cosmic structure grew. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which increased the gravity further, in a runaway process that eventually created galaxies and galaxy clusters. Regions that were slightly less dense than average became the cosmic voids, the vast, empty regions between the filaments of the cosmic web. These temperature fluctuations in the CMB weren't random. They have a characteristic pattern, a power spectrum that shows what sizes of fluctuations were most common. This pattern was determined by physical processes in the early universe. Pressure waves propagating through the plasma before recombination, quantum fluctuations stretched to cosmic sizes during inflation. By measuring this pattern precisely, cosmologists can determine fundamental properties of the universe: its age, its composition, its geometry. The CMB has revealed that the universe is approximately 13.8 billion years old. It's told us that ordinary matter, the stuff of stars and planets and people, makes up only about 5% of the total mass-energy content of the universe. Dark matter, which interacts with ordinary matter only through gravity, accounts for about 27%. And the remaining 68% is dark energy, that mysterious component driving the accelerated expansion of space. But the CMB has also revealed anomalies, features that don't quite fit our standard models of cosmology. The most famous of these is the axis of evil, a peculiar alignment of the largest temperature variations in the CMB that seems to point in a specific direction in space. In our standard model of cosmology, based on the assumption that the universe is homogeneous and isotropic on large scales, there should be no preferred direction. Every direction should be statistically equivalent. Yet, when astronomers measure the CMB, they find that the largest scale temperature variations, the ones spanning wide swaths of the sky, seem to be aligned with each other and with the plane of the solar system. This correlation has persisted through multiple independent observations by different satellites: COBE, WMAP, and Planck. It could be a statistical fluke, the result of analyzing a finite amount of data. Or it could be telling us something profound about the universe. That perhaps it's not quite as isotropic as we thought, that there really is a special direction in space. Then there's the cold spot, a large region of the CMB that's significantly colder than its surroundings, larger and colder than should occur by random chance in our models. Some cosmologists have suggested it might be the signature of a collision with another universe, a bubble universe from the multiverse pressing up against our own. Others think it might be a supervoid, an extraordinarily large, empty region of space through which the CMB photons passed, losing energy as they climbed out of the void's gravitational potential. Or it, too, could simply be a statistical fluke, one of those unlikely things that's bound to happen when you have enough data. More recently, there's been growing discussion of the cosmic dipole anomaly. The CMB isn't quite the same temperature in all directions. There's a subtle pattern, a dipole, where one hemisphere of the sky is slightly warmer than the other. This is easily explained by our motion through space. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way is falling toward the Virgo cluster, and so on. All these motions combine to give us a velocity of about 370 kilometers per second relative to the cosmic microwave background. Because of the Doppler effect, the CMB appears slightly hotter in the direction we're moving toward, and slightly cooler in the direction we're moving away from. But here's the puzzle. When astronomers measure the motion of galaxies and galaxy clusters on large scales, the directions and speeds don't quite match up with the CMB dipole. It's as if the matter distribution in the universe is flowing in a slightly different direction than expected, or with a different speed. This cosmic dipole anomaly might indicate some large-scale structure or flow in the universe that we haven't accounted for. Or it might suggest that our standard model, which assumes perfect isotropy on the largest scales, needs refinement. These anomalies in the cosmic microwave background are subtle, and their significance remains debated. They might all be explained away with better understanding of systematic errors in our measurements, or with more sophisticated statistical analysis. Or they might be the first hints that our cosmological models, successful as they've been, are missing something important about the nature of the universe on the largest scales. When you look at the cosmic microwave background, you're seeing the edge of the observable universe in time. You're looking back to an era when the cosmos was just a tiny fraction of its current age, when it was hot and dense and uniform. But you can't see past this surface. Earlier than 380,000 years after the Big Bang, the universe was opaque to electromagnetic radiation. The CMB is, in a very real sense, a wall that blocks our view of earlier times, except that it's not quite a complete wall. There are two other messengers from the early universe that can penetrate farther back than the CMB: neutrinos and gravitational waves. Neutrinos interact so weakly with matter that they could have been traveling freely through the cosmos since it was only 1 second old. Gravitational waves, ripples in the fabric of space-time itself, could have been propagating since the very moment of the Big Bang. If we could detect these primordial neutrinos or gravitational waves, we could peer back to even earlier epochs, perhaps even to the moment of inflation itself. Some experiments are already searching for these signals. The BICEP and Keck-array telescopes at the South Pole look for a subtle pattern in the polarization of the cosmic microwave background that would be the signature of primordial gravitational waves from inflation. So far, they've set limits on how strong these waves could have been, but haven't detected them definitively. Future gravitational wave observatories, both on Earth and in space, might be able to detect these echoes from the first moments of the universe directly. For now, though, the cosmic microwave background remains our deepest direct view into cosmic history, our most ancient window on the universe. It's a wall of light that surrounds us at the edge of the observable universe, carrying information encoded in tiny temperature variations about the conditions in the infant cosmos. Every time we refine our measurements of the CMB, we learn something new about the universe's composition, its age, its geometry. We're reading the baby pictures of the cosmos, decoding the pattern of sound waves that rippled through the plasma 13.8 billion years ago. And every measurement raises new questions. Why is the universe so uniform? Why does it appear to have anomalies that hint at violations of perfect isotropy? What happened before recombination, in those first 380,000 years when the universe was opaque? What happened even earlier, in the first second, the first microsecond, the first inconceivably tiny fraction of a second after the Big Bang? These questions lead us deeper still, beyond the observational edge of the CMB to the theoretical frontiers where we try to understand not just what the universe is, but why it exists at all. Dark energy and the accelerating universe. In 1998, two teams of astronomers made a discovery that would fundamentally change our understanding of the universe and would earn them the Nobel Prize in Physics. They were studying type Ia supernovae, the spectacular explosions of white dwarf stars in binary systems, using them as cosmic distance markers to measure how fast the universe was expanding at different times in cosmic history. The expectation was clear. The universe had been expanding since the Big Bang, but that expansion should be slowing down over time due to the gravitational attraction of all the matter in the cosmos pulling back on itself. The only question was how fast it was slowing. Was there enough matter to eventually halt the expansion and reverse it, leading to a big crunch? Or would the expansion continue forever, gradually slowing but never quite stopping? But the data told a different story. The distant supernovae, whose light showed the universe as it was billions of years ago, were dimmer than expected. They were farther away than they should have been if the expansion were slowing down. The only way to make sense of this was to conclude something that seemed impossible. The expansion of the universe wasn't slowing down at all. It was speeding up. This accelerating expansion demands an explanation. In Einstein's equations of general relativity, to make the universe expand faster and faster, you need something with negative pressure, something that pushes outward on space rather than pulling inward like normal matter. This mysterious component, making up nearly 70% of the total mass energy content of the universe, was given the name dark energy. We don't know what dark energy is. After nearly 3 decades of study, it remains one of the deepest mysteries in physics. The simplest possibility is that it's a cosmological constant, a property of space itself, a uniform energy density that fills every cubic centimeter of the universe with the same amount of energy. In this picture, dark energy doesn't change over time or vary from place to place. It's just a constant background field that's always been there and always will be, becoming more important as the universe expands because matter and radiation get diluted with expansion. But the energy density of the cosmological constant stays the same. Albert Einstein actually introduced a cosmological constant into his equations back in 1917, not to explain accelerating expansion. The expansion itself hadn't been discovered yet, but to create a static universe that neither expanded nor contracted. When Edwin Hubble discovered that the universe was expanding in 1929, Einstein removed the cosmological constant, reportedly calling it his biggest blunder. Now, it seems, the cosmological constant has made a comeback, though not quite in the form now. It seems the cosmological constant has made a comeback, though not quite in the form Einstein originally envisioned. Instead of a force to keep the universe static, it is the very engine driving its runaway expansion. As you settle deeper into your surroundings, imagine this dark energy not as a substance, but as the inherent cost of space itself. Every cubic centimeter of the void, every empty inch between your hands, contains a tiny, persistent push. In the early stages of the cosmos, when matter was packed tightly together, gravity was the undisputed king, slowing the expansion and drawing galaxies into a cosmic web. But as the universe grew, the density of matter thinned out, while the density of dark energy remained constant. About 5 to 6 billion years ago, the balance tipped. The outward push of the vacuum began to overpower the inward pull of all the stars and dark matter in existence, and the universe began to fly apart at an ever-increasing rate. But is this energy truly a constant? This is where the most recent and perhaps most unsettling discoveries come into play. Recent data from the Dark Energy Spectroscopic Instrument, DESI, suggests that dark energy might not be a static property of the vacuum. It might be evolving. If dark energy is quintessence, a dynamic field that changes over billions of years, then the edge of our universe is far more unstable than we imagined. If its strength increases over time, we move toward a big rip. In this scenario, the acceleration becomes so violent that it eventually overcomes the gravity holding galaxies together, then the electromagnetic forces holding planets, and finally, the nuclear forces holding atoms together. The fabric of reality would literally be shredded at the edge of time. Conversely, if dark energy remains a constant, we face the heat death. The edge of our observable universe will effectively shrink. Galaxies that we see today will one day cross our cosmic event horizon, moving away from us faster than light can travel back to us. One by one, the lights of the cosmos will go out. Future civilizations, if they exist, will look up at a sky that is completely black, devoid of any stars or galaxies beyond their own local group. The edge of the universe will have moved so far and so fast that it leaves us in total isolation. Understanding dark energy is the key to knowing how much time the universe has left. It dictates whether the edge is a permanent boundary or a receding curtain that will eventually leave us in darkness. As the expansion accelerates, the horizon of what we can ever hope to reach is pulling away from us at millions of miles per second, making our observable bubble a lonely island in a sea of expanding nothingness. As you settle deeper into the quiet stillness of your room, let your mind drift past the final glowing embers of the observable universe. We have reached the 46.5 billion light-year mark, the limit of what the light from our Big Bang can reveal to us. But, as we have discussed, this is not a physical wall. It is a curtain of time. Imagine for a moment that you possess the ability to step beyond this curtain, to move instantaneously through the dark to a point 50 billion or even 100 billion light-years away. If you were to look around from that new vantage point, you would find yourself at the center of a new sphere of light, with new galaxies, new stars, and a new horizon stretching out exactly like the one we see from Earth. This realization forces us to confront a staggering possibility. Our entire observable universe, with its 2 trillion galaxies and its vast cosmic web, might be nothing more than a single grain of sand on a beach that stretches forever. This is the gateway to the multiverse. The most mathematically grounded version of this beyond comes from the theory of eternal inflation. To understand this, we must go back to the very first trillionth of a second after our Big Bang. During this era, space underwent a period of exponentially rapid expansion, stretching from the size of an atom to the size of a galaxy in a heartbeat. While this inflation stopped in our local pocket of space, allowing the hot plasma to cool and form the stars we see today, many physicists believe that inflation never actually stopped in the regions beyond our edge. In the vast, unobservable reaches of the outside, the vacuum of space is still doubling in size every fraction of a microsecond. This space is expanding much faster than the speed of light, acting as an ever-growing sea of pure energy. Within this sea, our universe is like a small bubble of stability that has formed in a boiling pot of water. Every so often, a small region of the eternally inflating vacuum slows down, shedding its energy and triggering a new Big Bang. This creates a bubble universe. But because the space between these bubbles is expanding so rapidly, no two bubbles can ever meet. They are forever isolated, drifting in a cosmic foam where the background is always growing, always birthing new realities. This means that beyond our 46.5 billion light-year horizon, there are trillions upon trillions of other bubbles, each containing its own vast expanse of space and time. This brings us to the string theory landscape, an idea that adds a layer of infinite variety to these bubble universes. String theory suggests that there are as many as 10 $500 different ways that the fundamental dimensions of space can be folded or compactified. Each of these ways produces a different set of physical laws. In our specific bubble, the strength of gravity, the charge of an electron, and the mass of a proton are perfectly balanced to allow for the complex chemistry of life. But in the bubble next to ours, gravity might be so overwhelmingly strong that the entire universe collapses back into a singularity mere seconds after its birth, a local Big Crunch. In another, the force that binds atoms together might be so weak that matter never forms at all, leaving a universe that is nothing more than a cold, lonely mist of subatomic particles drifting in total darkness. As you breathe slowly and let these thoughts wash over you, consider the staggering implications of an infinite multiverse. If space is truly infinite beyond our edge, then every possible arrangement of matter must occur somewhere. This is the Level 1 multiverse, regions of space so distant that they are beyond our light horizon, yet part of the same continuous fabric of space-time. Because there are only so many ways you can arrange atoms in a given volume of space, an infinite universe dictates that eventually the patterns must repeat. Somewhere, trillions upon trillions of light-years beyond our edge, there is another version of the Milky Way, another solar system, another Earth, and another version of you, lying in a bed identical to yours, listening to these very same words. This concept is both beautiful and terrifying. It suggests that every choice you have ever made, every path you have taken, is mirrored by a version of yourself in another part of the multiverse who chose differently. It robs our personal existence of its perceived uniqueness, yet it also provides a profound answer to the fine-tuning problem. Why are the laws of physics so perfect for us? In a multiverse, they aren't perfect because of design. They are perfect because we happen to live in one of the rare bubbles where the laws allow for observers to exist. We are like travelers who have found a rare oasis in an infinite, inhospitable desert. The multiverse isn't just a theoretical playground. It might have left physical evidence on our own cosmic horizon. Astronomers studying the cosmic microwave background have discovered a cold spot, a vast region of the sky that is significantly colder than our models predict. Some cosmologists have suggested that this cold spot could be a bruise left behind by a collision with another bubble universe in the distant past. If our universe bumped into another during the era of inflation, the impact would have left a permanent ripple in the temperature of the infant cosmos. Similarly, the axis of evil, a strange alignment in the CMB's temperature fluctuations, might be a hint that our universe is being pulled or influenced by a massive structure existing just beyond our observable edge. As we ponder this, the edge of the universe stops being a boundary and becomes a threshold. We are no longer looking at a simple container of stars. We are looking at a single cell in a vast living organism of infinite growth. The multiverse suggests that the Big Bang was not a unique event, but one of an infinite number of firecrackers going off in a dark, eternal field. Every time you look up at the night sky, you are seeing the limit of your own eyes, but your mind can now see much further. You can see the bubbling foam of infinite realities, each with its own history, its own laws, and its own destiny. In the silence of the night, this vastness can feel overwhelming, but let it instead be a source of peace. The universe, and the multiverses beyond it, are so large that our individual worries and the tensions of our day become smaller than the smallest atom. We are part of a grand, eternal dance that has no beginning and no end. We are the witnesses of a mystery that stretches into infinity, a reality that is far more diverse, far more chaotic, and far more magnificent than anything we could have imagined. As you drift toward sleep, carry this image with you, a sea of infinite bubbles, glowing with the light of 1,000,000,000,000 Big Bangs, each one a testament to the fact that existence is boundless, and that beyond the edge of what we see, the story of the universe continues forever. The holographic principle. As we venture further into the cosmic silence, passing beyond the bubbling foam of the multiverse and the infinite pockets of eternal inflation, we encounter perhaps the most mind-bending concept in all of modern physics, the holographic principle. This theory does not just ask what lies at the edge of the universe, it asks what the edge is. To our human senses, the world is a three-dimensional stage, a vast space of depth, height, and width where we move, breathe, and exist. But the holographic principle suggests that this 3D reality is an elegant illusion, a sophisticated projection emerging from a two-dimensional surface located at the very edge of the cosmos. It proposes that all the information required to describe our entire universe, every star, every planet, and every thought you have ever had, is actually encoded as a flat, 2D dataset on the distant cosmic horizon. To grasp the magnitude of this idea as you drift toward sleep, imagine a common credit card in your hand. On its surface is a small, flat, two-dimensional sticker called a hologram. When you tilt the card, a three-dimensional image appears to jump out at you, possessing depth and detail that seem to occupy space. Yet, you know that the depth you see is not actually there. It is a clever projection of information stored on that flat, 2D surface. The holographic principle suggests that our entire universe is functioning on this exact logic. The bulk of our 3D world is merely a projection of bits of information residing on the boundary of the universe. This concept was not born from idle speculation, but from the rigorous study of the most extreme objects in the known universe: black holes. In the 1970s, physicists like Stephen Hawking and Jacob Bekenstein stumbled upon a paradox regarding what happens to information when it falls into a black hole. According to the laws of quantum mechanics, information can never be truly destroyed. However, when an object falls into a black hole, it seems to vanish from our reality forever. Bekenstein made a startling discovery. When an object enters a black hole, the information it carries is not lost in the volume of the hole. Instead, it is smeared across the surface of the event horizon. He found that the information capacity of a black hole, the maximum amount of data it can hold, is proportional to its surface area, not its volume. In our everyday world, if you want to know how many books a library can hold, you measure the space inside the building. But in the strange holographic language of the cosmos, the number of books depends only on the surface area of the walls. This led to the Bekenstein bound, a fundamental limit on how much information can be contained in any given region of space. If a black hole stores its secrets on its outer shell, then perhaps the entire universe, the ultimate black hole in a sense, does the same. This idea was mathematically solidified in 1997 by Juan Maldacena through the ADS-CFT correspondence. He demonstrated that a mathematical model of a universe with gravity in 3 dimensions could be perfectly described by a quantum field theory with no gravity in only 2 dimensions. This was the Rosetta Stone of modern physics, showing a definitive link between the boundary and the bulk. It suggests that space itself might not be fundamental. Instead, space is an emergent property, much like the temperature of a gas emerges from the motion of individual atoms. In this view, the edge of the universe is the only place where reality is truly written, and everything we experience is the reading of that data. Consider what this means for the nature of the edge as you relax into the stillness of the night. The edge is no longer just a faraway limit where light fails to reach us. It becomes the most vital, information-dense part of existence. It is a vibrating, fluctuating membrane of pure quantum data, where every event in cosmic history is inscribed. If you could travel to this edge, you wouldn't find a void. You would find the source code of reality itself. Every interaction, every movement of a subatomic particle, and every flicker of a distant star is a calculation being performed on that 2D surface, which we perceive here as 3D action. This changes our perception of distance and separation. In a holographic universe, the concept of far away becomes a matter of perspective. If the information for a galaxy 10 billion light-years away is written on the same surface as the information for the bed you are lying in, then, in a very real sense, all points in the universe are interconnected at the boundary. This provides a hauntingly beautiful explanation for quantum entanglement, the spooky action at a distance, where 2 particles remain linked across vast expanses. They aren't communicating across space. They are simply 2 points on the 3D projecting as you breathe slowly. Let the illusion of the physical world soften. You are not just a collection of matter moving through an empty container of space. You are a living, breathing manifestation of a cosmic archive. The holographic principle invites us to see the edge of the universe not as the end of the world, but as the beginning of it. It suggests that reality is far more fluid, far more digital, and far more interconnected than our senses lead us to believe. We are the witnesses of a grand cosmic cinema, where the film is playing on the horizon of the universe, and we are the characters brought to life by its light. On that share the same underlying data on the 2D surface. The universe's edge, therefore, is the ultimate mirror. It is the place where the laws of physics are recorded, and where the mystery of existence is safely stored in the language of light and information. In the quiet of the night, realize that you are never truly separate from the edge of the universe, because the edge is the very place where your story is being written. As you drift toward sleep, carry the peace of knowing that you are part of a grand architecture that is far more stable, far more intricate, and far more wondrous than any 3D world could ever be. Section 8. James Webb's View, Peering Toward the Beginning. As we continue to float through the cosmic depths, our minds filled with the theoretical wonders of holograms and multiverses, we find ourselves needing a lighthouse, a physical eye that can confirm the whispers of the ancient past. That lighthouse is the James Webb Space Telescope, JWST. Stationed nearly 1,000,000 miles from Earth at a stable point in space called L2, it sits in the cold, dark silence, turning its massive golden mirror toward the very edge of our observable reality. Webb is more than just a telescope. It is a time machine, designed to capture photons that have been traveling through the void for over 13 billion years. To understand the magnitude of Webb's vision as you relax into your bed, you must first understand the nature of the light it seeks. The universe is expanding, and as it expands, it stretches the light traveling through it. Light that began its journey as high-energy ultraviolet or visible light from the very first stars has been stretched by the stretching fabric of space-time itself. By the time these photons reach our solar system, their wavelengths have grown so long that they have shifted out of the visible spectrum and into the infrared, the spectrum of heat. Human eyes cannot see this light, but Webb was built specifically to feel its faint, ancient warmth. When Webb first opened its golden eye and pointed it toward a seemingly empty patch of the sky, it revealed a universe that was far more crowded, vibrant, and complex than we ever dared to imagine. In the famous deep field images, every tiny, smeared spark of light is not a star, but an entire galaxy containing billions of suns. Some of these galaxies are seen as they were just a few 100 million years after the Big Bang. This is an era cosmologists call the cosmic dawn, the moment when the very first stars flickered to life, ending the dark ages and bathing the universe in its first light. One of Webb's most shocking discoveries is a galaxy known as JD's GS-Z.0. It is a ghost from the beginning of time, appearing to us as it was a mere 290 million years after the Big Bang. According to our standard models of how the universe grew, a galaxy this large and this bright shouldn't have been able to form so quickly. It suggests that the early universe was a much more efficient engine of creation than we predicted. It's as if we expected to find a nursery of tiny, fragile sparks, and instead found a landscape of roaring wildfires. These impossible galaxies are forcing scientists to reconsider the role of dark matter and the speed at which supermassive black holes grew at the universe's edge. As you breathe slowly, imagine the journey of a single photon captured by Webb's mirror. It began its voyage in a violent, high-energy environment shortly after the universe became transparent. At the moment of recombination we discussed earlier, it has spent the last 13.5 billion years racing through an ever-widening void, passing by the births and deaths of countless stars, narrowly avoiding the gravitational traps of black holes, all while the very space it traveled through was expanding beneath it. After an eternity of travel, it finally hits a segment of Webb's 6.5-meter mirror, is reflected into a sensor and becomes a single pixel in an image that reveals the dawn of time to a curious species on a small blue planet. Webb is also peering into the mysterious Ryanization era. Before the first stars, the universe was filled with a thick, neutral hydrogen fog that blocked most light. As the first massive stars turned on, their intense radiation burned through this fog, turning the hydrogen into a transparent plasma. Webb is watching this process happen in real time, observing the bubbles of transparency growing around the first galaxies. It is showing us the literal clearing of the cosmic sky. This vision brings us to the very limit of what light can ever tell us. Webb is pushing us right up against the wall of the cosmic microwave background, that orange-red glow of the infant universe. Beyond that, light cannot go. But Webb's discoveries suggest that the edge is not just a place where things end, but where the most intense and formative actions took place. Every time Webb finds a galaxy further back than the last, it adds a new chapter to the story of our origins. Peering through Webb's lens, the universe feels less like a cold, empty void, and more like a vast, unfolding tapestry. We are seeing the seeds of everything that would ever exist. The carbon in your bones, the oxygen you are breathing right now, the iron in your blood, all being forged in those first ancient stars that Webb is just now bringing into focus. The edge of the universe is not just out there, it is the beginning of us. As the golden mirror of Webb continues its silent vigil in the darkness, it reminds us that the more we see, the more we realize how much is still hidden. The mysteries are multiplying. Why did the first galaxies grow so fast? What role did dark energy play in those early moments? With every image, Webb is inviting us to look deeper, to stay curious, and to realize that the edge of the universe is a horizon that keeps moving, challenging us to follow it into the infinite unknown. As you drift closer to sleep, let the images of those distant, glowing jewels fill your mind. You are witnessing the very first light of creation, captured by a human-made eye standing guard at the edge of the dark. The universe is ancient, vast, and full of wonder, and you are a part of the generation that finally got to see its beginning. The ultimate mystery, what lies beyond. We have reached the absolute precipice of our cosmic journey, standing at the final boundary where light, mathematics, and human observation begin to dissolve into the unknown. Behind us lies the observable universe, a vast, shimmering sphere 93 billion light-years across, filled with the debris of ancient stars and the whisper of the Big Bang. But before us lies the ultimate mystery, the question that has haunted every civilization since our ancestors first looked up at the night sky. What lies beyond the edge? It is here, at this theoretical and physical threshold, that we must confront the limits of being human and the staggering scale of a reality that may not have been designed for us to fully comprehend. The honest answer, the one that humbles every astronomer and physicist, is that we simply do not know. Because the universe has a finite age and light has a maximum speed, there are regions of space that are, by their very definition, beyond our reach. Their light hasn't reached us yet, and in a universe dominated by accelerating expansion, it may never arrive. This creates a profound philosophical silence at the edge of everything. If the observable universe has a radius of 46.5 billion light-years, what exists at a distance of 50 billion or a trillion? Is it more of the same? More galaxies, more voids, more clusters, stretching out in an infinite, flat plane? Or does the nature of space-time undergo a fundamental shift once you cross the horizon of our local bubble? In the absence of direct observation, we turn to the beauty of our equations, which suggest several possibilities, each more mind-bending than the last. One possibility is that the universe is truly infinite, extending forever in all directions without end or boundary. In such a universe, the edge is merely a subjective viewpoint, a curtain that moves with the observer. If this is the case, the implications are staggering. In an infinite space with a uniform distribution of matter, every possible arrangement of atoms must occur somewhere. Somewhere beyond our horizon, there could be an infinite number of exact copies of this very moment, with an infinite number of observers asking these same questions. This idea robs our reality of its uniqueness, turning our entire history into just one line of code in an infinite, repeating book. Another possibility is that the universe is finite but unbounded. Like the surface of a sphere, you could travel forever in one direction and never hit a wall, eventually returning to your starting point. This would mean that the edge is a topological illusion, a place where space curves back on itself so gently that we perceive it as flat. Recent hints of positive curvature in the cosmic microwave background data suggest that we might live in such a closed universe, a vast hypersphere hundreds of billions of light-years across. In this scenario, there is nothing outside the universe because space and time themselves only exist within the sphere. There is no beyond, only a loop of existence that contains everything. But what if the edge is something more radical? What if our entire four-dimensional space-time is just a membrane floating in a higher dimensional void, as some versions of string theory suggest? In this brain world scenario, the ultimate mystery is that we are trapped on a thin slice of a much larger reality. The things we cannot see, dark matter, dark energy, or the missing pieces of our equations, might be leaking in from these higher dimensions. The edge would not be a distance in space, but a direction we cannot point to, a hidden depth to reality that our senses were never evolved to perceive. As you drift closer to sleep, consider the peace that comes with this uncertainty. Living with the ultimate mystery is not a sign of failure, but a testament to the scale of the cosmos. We are a young species, barely out of our atmospheric cradle, and yet we have managed to map the echoes of the Big Bang and measure the expansion of the heavens. The fact that there is still an edge, still a beyond, means that the story of discovery is never ending. It means that no matter how much we learn, the universe will always be stranger, larger, and more magnificent than we can imagine. The ultimate mystery is the final frontier, the place where science ends and wonder begins. It reminds us that we are part of something truly boundless, an architecture of light and gravity that spans distances we can only name, but never truly feel. As the lights of our local group of galaxies slowly dim over the coming trillions of years, and as more of the universe disappears beyond our event horizon, this mystery will only deepen. But for tonight, it is enough to know that the edge is there, guarding the secrets of the infinite, and that you are a conscious part of this grand, unfolding dream. In the silence of this mystery, all the tensions of the day fall away. The complex math, the vast distances, and the accelerating expansion of the void all become a gentle background hum, like the distant sound of waves on a cosmic shore. You are safe within your observable bubble, anchored to a planet that is moving through a mystery it has only just begun to understand. Let the beyond be a place of quiet curiosity, a dark and beautiful sanctuary for your mind to rest. There are no more questions to answer tonight, no more horizons to cross. The edge of the universe is waiting, and it is more beautiful than you can ever imagine. Closing meditation. Now, let the journey conclude. Bring your awareness back to the gentle rhythm of your breath, the rise and fall of your chest, as the vastness of the cosmos begins to settle around you like a soft, velvet blanket. We have traveled through the particle horizon, past the surface of last scattering, and into the theoretical realms of the multiverse and the holographic edge. But now, the stars are fading into a soft, warm glow. The 93 billion light-year diameter of our observable home is contracting back to the peace of this single moment, here in your room, where you are safe, still, and calm. The atoms that make up your body were forged in the hearts of stars that now sit billions of light years away at the edge of our vision. You are not a stranger to the universe. You are its own consciousness, looking back at the beginning of time. As you prepare for a deep, restorative sleep, let the knowledge of our cosmic home provide you with a sense of profound belonging. The universe is large, but you are a vital part of its tapestry. The mystery of the edge is not something to fear, but a vast, silent lullaby that sings of infinite possibilities. Release the last of your thoughts. Let the expanding fabric of space carry away any remaining stress, stretching it so thin that it disappears entirely into the background. You are floating in a peaceful void, a sanctuary of darkness where the only light is the soft, fading echo of your own wonder. In this space, time has no meaning, and the beyond is simply a place of rest. Thank you for journeying to the edge with us tonight. If you enjoyed this voyage through the stars, please consider subscribing to join us for future explorations of the unknown. But for now, let the screen of your mind go dark. Let the silence of the ultimate frontier guide you into the deepest of dreams. The edge of the universe is strange, beautiful, and vast, and it is now time to sleep. Good night.